So we said an LLM predicts the next word. But to predict the next word well, it needs to have seen a lot of words first. And when I say a lot, I need you to recalibrate what a lot means. One of the largest publicly available training datasets is called FineWeb, put together by a company called Hugging Face. It contains 15 trillion tokens of text. That's roughly 44 terabytes of pure text data. No images, no videos, just words. To put that in perspective, if you sat down and started reading this text non-stop, 24 hours a day, 7 days a week, it would take you over 2600 years just to read it once. And that's not even the biggest dataset out there. The frontier models train on far more than this. So where does all this text come from? Basically, the internet. Web pages, Wikipedia articles, books, research papers, Reddit threads, news articles, forum posts, Stack Overflow answers, GitHub code. If it was written down and publicly accessible on the internet, there's a good chance some version of it ended up in a training dataset. Now, the model doesn't memorize all of this text word for word. We'll get to that later, but it processes all of it. It sees all of it, and from all of that text, it starts to absorb patterns. But before the model can learn anything from this ocean of text, it needs to read it. And here's the thing, it doesn't read the way you and I do. You and I read words, the model reads tokens. A token is just a chunk of text. Sometimes a token is a whole word, sometimes it's part of a word, sometimes it's just a single character. Take the word understanding. You read that as one word. The model might break it into these 3 tokens. Or take the word the. That's common enough that it's just one token all by itself. And a rare or technical word like cryptographic that might get split into these 2 or even more pieces. Why does it do this? It's a practical compression trick. If you tried to give the model a separate entry for every possible word, including every name, every typo, every technical term in every language, you'd end up with a dictionary of millions and millions of entries. That's too much to work on. Instead, you break words down into common, recurring chunks. Most languages can be represented with a vocabulary of around 100,000 tokens. It's a much more efficient way to handle the enormous variety of human language. So when the model reads a sentence like this, what it actually sees is a sequence of token IDs. Something like this. Just numbers. Everything from here on out, the entire learning process, the entire intelligence of the system runs on these numbers, not words, numbers. Keep that in the back of your mind. It will matter a lot when we talk about how the model works on the inside. Alright, so we've got our mountain of text and we've chopped it up into tokens. Now comes the part where the model actually learns. And the training game is beautifully simple. Here's how it works. You take a sentence from the training data. You hide the last word. You show the model everything before it. And you ask, what do you think comes next? The model makes a guess. Maybe it says dog with 15% probability and Matt with 5% probability. Then you reveal the actual answer, Matt. And you tell the model, here's how wrong you were. Adjust yourself. That's it. That's the game. Hide a word, guess, check, adjust, repeat. Now do that billions of times across trillions of tokens of text, and this is where it gets mind-bending. At first, when the model is brand new, before any training, all of its internal settings are completely random. It's like a newborn. You show it the cat sat on the and it might guess purple or finance. Complete nonsense, it has no idea. But after the first 1,000 examples, it starts to pick up something. Maybe it learns that some words are just more common than others. After 1,000,000 examples, it's getting basic grammar right. After 1,000,000,000, it's picking up facts, relationships between concepts, writing styles. And after trillions of examples, it can predict the next word well enough to write your emails explain your tax code, and summarize a research paper. All from the same simple game: hide, guess, check, adjust. And here's the part that I think is genuinely profound. No one sat down and programmed rules into this thing. Nobody typed, if the user asks about France, say Paris. Nobody wrote a grammar checker and plugged it in. Nobody created a database of facts. The model discovered all of that: grammar, facts, reasoning patterns, tone, style, on its own, purely by trying to get better at one task, predicting the next word. It turns out that if you want to predict the next word really well across all of human text, you have to develop something that looks a lot like understanding. You have to know that Paris is the capital of France. You have to know that not good means the opposite of good. You have to know that a legal document sounds different from a WhatsApp message. The model wasn't taught any of that explicitly. It emerged as a side effect of trying to play the prediction game really well. So now we know what goes in: trillions of tokens of internet text, and we know what the game is: predict the next word over and over. But we haven't talked about the machine that plays this game. What is the model actually? What does it look like on the inside? That's what we'll get into next.